Hello everyone, this is Dr. Chen. In this video, we will cover parts of Chapter 9 that focus on Lewis theory. Here we have a diagram taken from Chapter 9, Figure 9.1. What we learned in Chapter 8, Periodic Trend, is that metals have low ionization energy. In other words, metals are easy to lose electron, while nonmetals, on the other hand, have high electron affinity. In other words, nonmetals are easy to gain electron. So when a metal bonds with a nonmetal, it transfers electron to the nonmetal. The metal atoms then becomes a cation, while the nonmetal becomes an anion. These oppositely charged ions attract to one another, resulting in a bond called ionic bonding. We also learn in Chapter 8, Periodic Trends, that nonmetals have high ionization energy. They are difficult to remove electrons. So when nonmetals bond with another nonmetal, neither atom transfer electrons to one another. Instead, the two atoms shares electron, resulting in a bond called covalent bonding. Since metals have low ionization energy, they tend to lose electron easily. In a simple model for metals interacting with metals, we use an electron sea model. In other words, all the atoms in a metallic lattice pool their valence electrons together. These pooled electrons are no longer localized on a single atom. Instead, these electrons are delocalized throughout the entire metal. The positively charged metal atoms are then attracted to the sea of electrons, resulting in a bond called metallic bond. In Chapter 8, we learned that valence electrons are those electrons in the outermost principal energy level. So in this example, we use oxygen. The electron configuration is 1s2, 2s2, 2p4. The outermost shells is the n equal 2 shell, and we have a total of 6 valence electrons, 2 from the 2s orbital, 4 from the 2p orbital. So together we have 6 valence electrons. Since valence electrons are held loosely, and since chemical bonds involves the transfer or sharing of electrons between two or more atoms, valence electrons are most important in bonding. Therefore, in Lewis theory, we're going to focus on valence electrons only. Here, we use one dot to represent a valence electron. The dots are placed around the element symbol with a maximum of 2 dots per side. The Lewis structure for the period 2 elements can be drawn in similar format. Notice atoms with 8 valence electrons are particularly stable because they have a full outer level. In other words, they have 8 dots, 8 valence electron, and we call this an octet. Drawing Lewis structure for molecular compound, let me give you some examples. Here's the first example of H2O, water. So there are 2 electrons involved in each single bond. So we call these electrons that is localized in a bond, we call them bonding pair electrons. So what about these electrons? They're not involved in a bond. We call them lone pair electrons. So you're going to hear these terms bonding pairs, lone pairs quite frequently throughout both Chapter 9 and Chapter 10. Here's another example, O2. So here's the skeletal structure of O2. Now let's complete the valence electrons surrounding each oxygen, and we arrive at this particular structure. But what we also realize that is we can take 2 valence electrons from oxygen on the left to form a double bond between the 2 oxygen. So the final Lewis structure is the one on the right. We have oxygen sharing 1 double bond, and each oxygen has 2 lone pair electrons surrounding it. So this is the so-called octet rule, that the bonding atoms obtain stable electron configuration of 8 electrons in the outermost shell. So if I take a look at the oxygen on the left, it has a total of 8 valence electrons. I count 1, 2, 3, 4, 5, 6, 7, 8. Remember, each single bond has 2 electrons that's involved. Similarly, let's count the number of electrons on the oxygen on the right. I count 1, 2, 3, 4, 5, 6, 7, 8. So again, the oxygen on the right also have octet. So to draw the best Lewis structure to describe O2, this is the one, because each oxygen has fulfilled octet rule. All of them have 8 electrons. Here we have another example of molecular compound, HF, hydrofluoric acid. Okay, so what we see here are the following. We expose hydrofluoric molecule to an electric field. So the plate on the left is negatively charged. The plate on the right is positively charged. Is the positively charged part of hydrofluoric molecule, namely the hydrogen part, will face towards the negatively charged electric field, while the fluorine part of hydrofluoric molecule, which is negatively charged, will face towards the positive charge electric field. So what this indicates to us is the following, that the hydrogen side of the molecule must have a slightly positive charge and the fluorine side of the molecule must have a slightly negative charge. So how we represent this difference in electron density is the following. So I want you to focus on this arrow that resides directly above the HF symbol here. So the positive sign on the tail indicate that the left side of the molecule has a partial positive charge, and the right side of the molecule, the side that the arrow is pointing towards, has a partial negative charge. Similarly, the delta positive sign represent a partial positive charge, and the delta negative sign represent a partial negative charge. So what these two arrows and also delta positive and delta negative symbol represent is the electron density is greater on the fluorine atom than on the hydrogen atom. So some definitions here. Electronegativity is the ability of an atom to compete for electron with other atoms to which it is bonded. It is the ability of an atom to attract towards itself the electrons in a chemical bond. So what we see here, the overall trend of increasing electronegativity is going up a group and going to the right of the periodic table. So fluorine, for example, has electronegativity value of 4.0, which is the highest electronegativity. And francium has the lowest electronegativity value of 0.7. So we're going to use this general trend of electronegativity to help us to decide if we have a polar bond or a nonpolar bond, or perhaps a polar covalent bond, which is to be discussed later. So table 9.3 outline these 3 different type of bonds. If the difference of electronegativity is small, we have a covalent bond. An example is CO2. If the electronegativity difference is intermediate, between 0.4 to 2.0, we have what's called as polar covalent bond. The example we have here is HCl. I'd like to draw our attention back to electronegativity table earlier. So hydrogen have an electronegativity value of 2.1, while chlorine has an electronegativity value of 3.0. So the difference in electronegativity, 3.0 minus 2.1 is 0.9. So we have an intermediate electronegativity difference, and therefore this is a polar covalent bond. And we can use the same strategy to to calculate the electronegativity difference for an ionic bond, for example, NaCl. So again, let's go back to the electronegativity table. Na has the electronegativity value of 0.9, whereas Cl has the electronegativity of 3.0. So the difference between them, 3.0 minus 0.9, is 2.1. Therefore, NaCl is an example of an ionic bond. So let's take a look at a different way to present the information in table 9.3. So we have a pure covalent bond. Electronegativity difference is between 0 to 0.4, where electrons are shared equally. And on the other end of the spectrum, we have the electronegativity difference between 2, beyond 2. We have ionic bond, whereas electrons are transferred. And an intermediate between the two are what's called polar covalent bond, where electrons are shared unequally, such as the example that we see in HF hydrofluoric acid. The fluorine part is the more electronegative, whereas the hydrogen part is the more electropositive. Okay, so let's take a look at the rules for drawing Lewis structure. First, let's count the total number of electrons, including charge. And the charge can be positive, which then you will remove electrons, or the charge can be negative, which you will then add more electrons. Then you can draw a skeletal structure. The general rule of thumb is to put the least electronegative atom in the center. And hydrogen and fluorine are always terminal. In other words, they are at the end of each bond. They are on the outermost structure. And then we can deduct 2 electrons for each single bond that we drew earlier in step number 2. And then whatever is remaining of electrons, we will use it to complete octet of terminal atoms. And remember, there's only 2 electrons allowed for hydrogen. And then we can subtract electron that has been used to fulfill octet for terminal atoms. And whatever number of electrons that is remain, we can place it on the central atom. Finally, we can double check for ourselves, does the central atom have an octet? If not, you can use lone pairs to form double bond, and to form multiple bonds, and that may include invoking on double bond or triple bonds. But please note that often group 2A and group 3A elements have less than 8 electrons. We're going to see some example of these exceptions later. And then finally, especially in the case when there could be multiple Lewis structure drawn, we can use the calculation of formal charge to help us to decide which Lewis structure is the best Lewis structure. So formal charge, Fc, is calculated as the following: valence electron minus the sum of the number of non-bonding electrons and the number of bonds. And remember, all formal charges on the atom that make up this molecule must add up to the total charge of this molecule. Finally, if possible, we're going to minimize formal charges to 0 by creating multiple bonds. And we're going to talk about this later by going through some examples. So step 8 and step 9 may be new to you. I strongly encourage you to do as many examples from the end of chapter exercise on drawing Lewis structure as possible to help you familiarize yourself with these new rules. Okay, so we're going to go through 9 different examples of drawing Lewis structure. This is the first set, this is the second set, and finally the third set. So let's get started. Okay, the first example was P(F)(5). So let's count the total number of valence electron. In the phosphorus, let me just pull out the periodic table. Phosphorus is located here. And the electron configuration is bracket neon, 3s2, and then 3p3. So in other words, we have a total of 5 valence electrons. Okay. Similarly, if we take a look at fluorine, fluorine is located here. And the electron configuration for fluorine was 1s2, 2s2, and then 2p5. So the number of valence electron is 2 plus 5. We have a total of 7 valence electrons. So for fluorine, we have 5 valence electron. And for phosphorus, there's 5 valence electron. And we have a total of 5 fluorine. Each fluorine contributes 7 valence electron, and there are 5 of them. 5 times 7 give you 35 electrons. So we have a total of 35 plus 5, 40 electrons. Let's draw a skeletal structure. Phosphorus, we're going to put that in the middle, surrounded by 5 fluorine. So I use up a total of 5 single bonds. Let me just use a different color to indicate that. 1, 2, 3, 4, 5. Okay, so I have 5 single bond, and each single bond has 2 electrons. So I've used up 10 electrons already. I need a total of 40 electrons. So that means I have a remaining 30 electrons that will go on the terminal atoms first until I fill the octet. So let's do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So now I have a total of, so I'm going to count these electrons like this. This is one lone pair, and I have a total of 15 lone pair. And each lone pair is 2 electrons. I have 15 of them, contribute to 30 electrons. So in total, I have 40 electrons. Now I'm done because it matched with the initial number of electrons that I calculated. Next, I'm going to calculate the formal charges. So formal charges on phosphorus. Number of valence electron on phosphorus is 5 minus the sum of non-bonding electron. So if you take a look at phosphorus, there is 0 non-bonding electron, and there's a total of 5 bonds. So 5 minus 5 is 0. So this is good. We have a formal charge on phosphorus equal to 0. Now let's move on to any of the fluorine. Valence electron on fluorine is 7 minus number of non-bonding electron on fluorine. So let me just use a different highlighter. So I have 1, I have 1, 2, 3, 4, 5, 6. I have a total of 6 valence electrons, 6 non-bonding electrons surrounding fluorine, and there's 1 bond. So 7 minus 7 is 0. So in other words, the formal charges on fluorines are all 0, 0, 0, 0, and 0. So is the formal charge on the central atom phosphorus. So this is excellent Lewis structure. You want the formal charge to be 0 if at all possible. So this is done. All right, so we're going to move on to the next example, and we have BRF5. So you can use the periodic table to help you figure out number of valence electron bromine is 7, and we have 5 fluorine. Each one contributes 7 electron to a total of 35. There's no charge on BRF5, so 7 plus 35 will give 42 electron. Okay, so let's draw the skeletal structure of bromine. 1, 2, 3, 4, 5. We have 5 single bond. Okay, we have 5 single bond, and each single bond has 2 electrons. There are 5 of them, add up to a total of 10 electrons. I need a total of 42. So I need 42 minus 10. So I have 32 electrons to go around the terminal atoms, in other words, fluorine first, to fulfill the octet. So let's try that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, so I've used up 30 already, but I actually have 32. So that means I have 2 more valence electron that is remain. And where we're going to put them? We're going to put them on the central atom bromine. Okay, so now let's count if we add up the number of electrons correctly. So remember, 2 electrons count as 1 lone pair. So we have a total of 16 lone pair electrons. Okay, so we have 32 electrons in total. So 10 plus 32 is 42 electrons. Okay, so this is correct. We have added the number of electrons correctly on Lewis structure. The next step is to calculate formal charge. So formal charge on bromine, number of valence electron on bromine is 7 minus number of non-bonding electron. So I see there's 1, 2. There's 2 non-bonding electrons on bromine. So I'm going to write 2. And there's a total of 5 bonds surrounding bromine. 1, 2, 3, 4, 5. So I have 5 here. So again, 7 minus 7 is 0. And you can apply the same calculation to fluorine. Number of valence electron minus the sum of non-bonding electrons plus the number of bonds, give you 0. So again, this is the correct Lewis structure. All the formal charges are 0, and they add up to the overall charge of this compound, BrF5, which is 0 charge, 0 overall charge. Okay, so you can move on and to do the final example from the first set of the example, SF4. So I'm not going to show you all the steps. Instead, I want you to stop the video and try this for yourself. Okay, so now you have a chance to try it. Hopefully you have the same Lewis structure for SF4 as the one that I drew here. You should have 4 single bond with a total of 13 lone pair electron. One of the lone pair is located on the central atom, sulfur. Okay, so now let's move on to the second set of Lewis structure example. So we're going to do CO2. Carbon have 4 valence electron, and there are 2 oxygen, and each oxygen has a total of 6 valence electron, add up to a 12. 12 plus 4 is 16 electron. So my first attempt of CO2, skeletal structure, carbon in the center, oxygen, oxygen. I use up 2 single bond, which is 4 electrons, and I should have 16 electrons. 16 minus 4, I have 12 remaining electrons to put on the terminal atoms to fulfill octet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and I'm done. Okay, let's calculate the formal charge on carbon. Valence electron is 4 minus number of non-bonding electron and number of bonds with a charge of plus 2. And we can calculate formal charge on oxygen. Number of valence electron minus number of non-bonding electron plus number of bond. So 6 minus 7 is minus 1. Okay, so let me just write the charge. This is positive 2. This is minus 1, minus 1. So minus 1 plus 2 and the minus 1 is equal to 0. So this is a correct Lewis structure. But we want it to be charge minimized. In other words, we want the formal charge to be as close to 0, if not 0, as possible. But what we see here is 1 is positive 2, 1 is minus 1. So this is not a charge minimized Lewis structure. So let's do another attempt. I'm going to take this lone pair electron oxygen and form a double bond. So this is my second attempt. Okay, so now I have 2 lone pair electron oxygen on the right. Let's calculate formal charge again. So formal charge on oxygen for this new second attempt is the following. 4 minus, there's no lone pair electron, and there's a total of 3 bonds. So this is slightly better. I have formal charge on carbon. Instead of 2, it's now 1. Formal charge on oxygen, I'm going to say oxygen on the left is equal to 6 minus 4 plus 2, which is 0. So this is clearly better. It used to be minus 1 in the first try. Oxygen on the right is still minus 1. Okay, so let's see if we can improve this by forming another double bond using a lone pair electron on oxygen. Okay, so let's calculate formal charge on the third attempt. So we have 0 formal charge on carbon. Formal charge of oxygen on the left and right are equal. They're both equal to 0. So this is the best charge minimized Lewis structure for CO2. Okay, so we have carbon double bond to oxygen on the left, and the same carbon also double bond to oxygen on the right. And the formal charge on oxygens and carbon are all zeros. 0, 0, and 0. Okay, so I would like you to try the next 2 examples by yourself. I want you to stop the video and try H2O and also SO3.